I would say almost 10 years, at least for parts of it. So it was a huge undertaking, and especially 3 parts of EDIs has been changed extensively. If we just start out with EDIs 5, it looks very, very similar to EDIs 4.8, and that is, of course, intentional. We think that big changes is enough. Also changing the interface would require even more work from the user side. So this is purely intentional, and we will focus on 3 on the most biggest changes. And that is the new zone model. And we will also look into an energy trading system and PV panels. But we will also show a few other features that has been changed. And there has been a lot of changes, but we will focus on these 3 big ones and just mention a few other ones. We will have time for questions. It will be moderated by Victoria. So if you type it in the chat window initially, and then we will take, and if we don't have enough time for questions afterwards, we will answer them in some other method, probably mail or something like that. But you will get the answers you need. Okay, so let me share my screen, and I will switch between the presentation and the EDIs. So hopefully this will work. You'll never know. We'll see about that. So, Victoria, can you see my screen, the presentation?
It's loading. It's loading. You might be on another screen.
Okay. Sorry about that. How about this?
Much better.
Okay, so let's begin. So we are going to talk about the zone model. And in EDIs 4.8, we had 2 zone models. We had the climate one and the energy. And they were pretty similar. There were some differences how radiation exchange was treated internally, but you could do most of the things with both. And we kept the energy for consistency, but the big limitation in the climate zone model, and that was that we could only treat rectangular boxes, has been changed. Now we can deal with arbitrary geometries as long as they consist of planar surfaces and the zones are closed. So now you could simulate any geometry in principle with a climate zone model. And that is, of course, very nice. But we also developed a completely new zone model called the Stratified Zone Model. And based upon the name, it's about stratification, so the temperature difference in height. And this opens up a lot of new possibilities. So we have the new, in the advanced tab under the zone model, we have a lot of new settings. For example, we have now in model fidelity the climate with stratification model. That's an option. And we have some previous things. We have, for example, the air velocity. It's similar, but new in this model is also that EDIs calculates the velocity in the zone. And this is done based upon something called, I'm going to change one thing here. So we have a lot of objects that affect the air temperature and the air velocity in the zone. So, for example, we have terminals, the supply terminals, most importantly. We have the humans, the heat loads, machines, computers, things like that. We have wall currents. hot and cold ones. We have a hot object, and the number of these objects affects the air movement or air speed inside the zone. And for you that has worked with CFD, this is kind of you get the similar possibilities, but this is not CFD. And then you can ask yourself, why didn't we go with CFD? Yes, we did. We are developing a CFD plugin for EDIs, but the downside with CFD is that it's very slow. It's detailed, yes, but in principle you can simulate with a powerful computer a single point in time, or maybe short period, a few minutes, but you can never simulate a day or a season or even a year. But with this new zone model, the stratified zone model in EDIs, you can simulate very detailed internal results in a reasonable amount of time. And this opens up a whole new series of problems that you can look at. For example, atriums, that's a big thing for us. So how do we deal with tall buildings? To do this, we model a number of layers. So we divide the zone height in layers. And this is on the upper right corner. You set the layer height, and then the zone is divided in layers. And for each layer, we calculate, most importantly, the temperature, but also the carbon dioxide levels and other metrics. And you can set these here under measures, what you are going to log, and you can log the temperature, the airspeed, radiant temperature, operative temperature, PPD, PMV, and so on. And it's quite similar to what you can log in CFD simulation. So, and then you can visualize these results in 3D. You don't need to log these measurements. The result will still, the stratification will still be simulated and treated the same. So the resolution does not really affect the result of the simulation. All it does is that affects what is visualized. And this is kind of what the result. So this is a difference between CFD and the stratified zone model, is that the mesh size in CFD actually affects the results. And we have some special settings to make this smooth. For example, you probably need to define all your supply terminals, where they are located, the airflow and so on, but you can also simplify it by using multipliers for these supply units. One big difference, and we will show that in a great example that Victoria has made for me, is that these flow elements, I didn't mention that, but we call them flow elements, these objects that affects the airflow. They do not interact with each other. So if you have two flow elements, for example, two terminals, supply terminals with the supply air towards each other, the air streams will just pass through each other, not affecting each other. So this is a big thing, and a limitation you need to be aware of. So let's look at the example. So let's assume we have a small office, a single zone office, and we're going to look at this both with the new zone model and with the CFD model. And the CFD model is currently in beta, but you can apply for, if you want to try it out, it will soon be a public beta. Until now it has been a closed one, but now we want everybody to play around with it and test it. So we have some, I can show you the image. So here is the office room, and we have a window over here. We have a small radiator, a big radiator. We have some internal loads in form of people, computers, the supply terminal over here. And then we have 4 layers. and we also log the results in a 1 decimeter resolution. And this simulation, here we see the airspeed in the results. So you see it's 0.3-ish in this area. And you can see here this is a cold case. So you have the cold draft, and you have the upward streams from the radiator, and then you have the convective loads that generates airspeeds from these internal loads, and of course the supply terminal. In this case, it's defined as a jet. This is the model we are currently using in EDICE for the new zone model. And we can look at the same thing for CFD. And you see here we have a geometry. We didn't have really a geometry here. We have more like points defining the location. So we also see that these 3-4 airstreams, the convection from these 4, they are interacting here. So you see that it looks a bit different, but in general, it looks kind of the same, but you also get the overall picture that is not shown here. The big airstream moving around here. We also see that we have some complexity in the roof here. We have small irregularity here that is not caught by the new zone model. So there are differences, but then we need to remember that this took 8 seconds to simulate for a whole day, and this took 100 seconds just for iterating the first 100 iterations, and it took 1 minute to do that, and then that is just 1 point in time. So this is the big difference. And there are cases where the zone model is probably more useful than not just for its simplicity and simulation speed, but also the result-wise, that there are things that is quite hard to capture with the CFD. We can show that maybe some other time. So this is we can look at also a bigger case. Let's look at an atrium. This is a big atrium. It's what is it? 24,000 cubic meters big, 1,200 square meters. Big windows. We have a lot of solar shading, and we have we have underfloor heating. We have heat pumps, and we also have a ventilation system that is carbon dioxide driven, variable airflow system. We have 200 visitors located in more or less 2 positions here. And we have, in this case, 1 meter layer height and a 0.5 meter cell resolution. And we save these 4 times per hour. So let's look at this in the wind case. So here we see the temperature distribution in height. So for every 0.5 meter, that was the layer height, we can look at the temperature over the day. We could also visualize this in 3D. This is the air speed in different layer heights. Well, it's not just layer height, it's in the whole. So you also see the effect of the facade here with the downdraft. And we see a few other things here as well. And we can animate this for time. So let's see here. So we can see here are the internal loads that keep changing because people come and go. And we also see the downdraft here. And well, we don't see it directly, but it's the air temperature here. So we see that it's colder near the facade. Of course, quite simple example, but still due to the size, this I would say would be very demanding to deal with in for a CFD simulation. So let's look at the same for the summer case. And here we see it's still not that interesting because it's a very good room. We have good efficient shadings, but here we see that the air temperature is varying a few degrees in height. We also can look at the operative temperature. And this is, of course, a big thing. So here is the operative temperature in various positions, and we see it's extremely homogeneous. The red one is the air temperature. And the reason that it's so homogeneous is that we have an efficient solar shading. So the radiant temperature is roughly the same. A bit more interesting maybe is the carbon dioxide levels, that in the top of the zone is maybe 900 ppm, but down where people actually are is more like 1,000 and even more. So this could affect the design depending on this result. And we can look at this as well for the summer, just for fun. And this is the air temperature that we are visualizing for this day. And we see here that this is the effect of the ventilation, and here we have the internal loads again. And here we also get a stratification. We knew about the stratification already since we looked at that charge, those charts before. So here we could, for example, deal with look at how we could reduce the ventilation flow rates and things like that, depending on just looking at the area where people actually is located. So that was a very short description, show a few examples of the new zone models. There is a lot of other things, but the most important thing that I would say is that the stratification that we've shown you, and also this that we can calculate the radiation exchange and operative temperature for irregularly shaped zones. We also have this concept of looking at the airflow, cold draft, and so on. You should be, as I mentioned before, a bit careful with that. It's mostly intended for getting the correct boundary conditions for the stratification, but as long as you have modeled it correctly by placing their terminals in the right positions, radiators, all objects, you can still use it for a number of things, but be a bit careful. And I would say that personally, well, we haven't released it yet, but if you're really going to use it for some big design changes, I would validate it with CFD as well, just for make certain that you have caught all the important aspects. So, yeah, so you probably start out with the new zone model, and if it's a really important design decision, I would validate it for some points in time with CFD. Okay, so that was the first big news in IDICE 5. The second one is the electrical system update, and we will look at a few ones. The first one is the battery. So a big thing in modern building is that they not just use energy, they also produce energy. And then we need to look at the whole system with production, and batteries is, of course, important aspect of these systems. So we have a new electrical system in IDICE. Before it was a part of the building, but now it's a separate system similar to air handling unit or plant. And we can here we have the electric battery, so we can insert that as an object. And we have here it is. So we have a few alternatives in the database. We have a few Tesla batteries, for example, and we have the possibility here to have them connected in parallel, the batteries, or we can have them in series. And why would you care about that? Well, it depends on what you want to use them for. So, for example, if you want them to last longer, you probably put them in parallel. And if you want to just have a big capacity, voltage, or yeah, you probably putting them in series. And right now it's a pretty simple controller. But this is something we are looking at providing more simple default controllers, and you can also create new ones yourself. And of course, this has a big impact on the result, depending on how you're going to control your batteries. And these are used for mostly for PVs, but also if you have wind turbines. So here they are. The second big update, well, the probably most important one, is the PV panels. And now, since if you remember, if you used this before, we already had a generic AC panel, and this hasn't changed. So it's a generic free size AC panel as before, and that's available from the electrical system. Previously, it was from the 3D. And this is a single piece only, as before. So you just define it by changing the size or the number of them. You have two variants. So you have the generic one, the old one, and you have something called ACPV freestanding panel, and that is an actual product. So now we have a product database as well, and you have them in the 3D as before, but it's still just a single one. But as I said, now we could have products as well. And you have a database with not a huge database. This is something we are working on, because the tricky part with PV panels is that the manufacturer keeps changing them. They keep adding and also renaming existing products, so it's a mess. So what we are looking at is to be able to simplify the way to add your own products, because I don't think we will ever be able to keep up with all the manufacturers. There will always be products that's not available in the database. So then you need a simplified way to add them, because it's quite a lot of parameters that needs to be defined for PV panels. They might look trivial on the outside, but they are not. And then the big thing, and that is the detailed AC and DC panel, and we have them as arrays. So now we are in the 3D view, and we have them collected afterwards in one table. If you're going with the AC, that's quite easy. There you have a homogeneous panel array. You have a built-in inverter. So they are quite easy to work with, but you can still place them. They are individually shaded, or they are shaded, so you can have a number of them on facades or roofs. Of course, it takes longer to simulate than a single one. We will look at that as well in a few minutes. But this is probably so. It's difficult which model you should pick one. It depends a little on what you are interested in. But if you're interested in how they are affected by nearby shading buildings or self-shading, I would say I would go probably with the detailed AC panel array model. And here is the table, so you can look at them individually if you like. And then we have, of course, the DC, and this is for me, I'm an HVAC engineer. I don't know much about PV panels, so this is for me a bit tricky, because you need to set them up, you need to string them, you need to add an optimizer, you need to, well, energy meters. Yes, you probably should attach different energy meters to different strings as well, so you can see how they operate individually. So this is more complex. You have individual or partially individual shading of these panels depending on how they are stringed. You can have optimizers. and a lot of you can really go into the details and see how they behave. But to make this useful, I would say that you need a consistent level of detail. So, for example, if you have this great resolution regarding the panels, you probably need it regarding the nearby shading objects, the air intakes, and all the things that are located on the roofs and nearby. And yeah, that could be tricky, especially in early stages. So you need to find a balance between these 3-4 models and which one to go with in the depending on what problems you are looking at. And here you can also you have the panels, and you can define the individual strings, and you can do the same for optimizers and the energy meters, and these are the ones that are mentioned in these red boxes. To make this a bit more simplified, there are ways to speed up. For example, this is an example that we have made for just using multipliers. So for AC panels, you can work with multipliers. So here we have just an example: 102 panels, evenly distributed on a roof and no shading. And this took 820 seconds to simulate. So some time, definitely. And you got some production, 32 gigawatt hours, if I see correctly. And if we just use multipliers, so what you do is that you build the system, and then you use this multiplier. So you have a parameter called mu, and you just type 102, and a single panel, and the result was, well, less than 0.5% difference, and this took 16 seconds. So yeah, there are great speed ups that can be made depending on the situation. But of course, this assumes that you don't have varying shading. Otherwise, this would probably not be a good idea. Well, maybe it would be a good idea, but you wouldn't be able to estimate that, and you wouldn't get the same result either. So yeah. Then comes the third part, and this is this is built upon what I said before, that buildings produce quite a lot of energy nowadays. And since they produce energy, we need to deal with that. How is that used, that energy production? And then we need to be able to trade energy. So we need to buy and sell energy. And now it gets tricky, because it's not obvious how this trading should be done. When is it beneficial to buy or sell? Because this varies depending on the situation. And this is from point in time, it changes. So what's useful in the nighttime or daytime it varies. And of course, it's also affected by the systems, for example, the batteries and things that we have already spoken of. So to make this possible, we have a whole new concept in EDIs, and these energy contracts and traders. And it's closely related to the energy meters that we had before, because this also affects the energy usage of the building, at least from a legal point of view. So we have added on the first page, we have these energy contracts and traders objects that can be found just below energy meters. And we also have a lot of new energy meters to make this possible. So here we have the traders and the contracts. So we are going to describe this in some detail, how this works. So we have something called assessment boundary, and this is a very important concept. So you have a kind of imaginary boundary, and this boundary defines if energy that passes through this is treated as delivered energy and is reported. So if you look at the delivered energy report, this is highly connected with this assessment boundary. So you can be on the inside of the boundary, you can be on the outside of the boundary. And for example, I'm no expert in the Finnish building code. Fortunately, my colleagues are. But here we have some concepts. So are you on the inside or the outside? And this is not obvious. So this is something you need to take into account as well. So we have this imaginary boundary, and then we also have something called utility, and that is the supplier of energy sources, and they are always available. So the society or the utility providers cannot run out of energy. And to make this possible, we have energy contracts, and you have contracts for purchasing and exporting and trading. And purchasing is buying from the outside, and export is sell to the outside of this assessment boundary, and then we can trade, and that is that it can be bidirectional, so you can and be within the boundary. So you have the possibility to trade inside as well. And to make this possible, we need contract rate plans, and that is a cost. So how much does the energy cost per kilowatt hour? And this could vary, but this is what drives the whole trading system. That is the cost. So you cannot, so you need to use the cost somehow. So you cannot optimize it. So say that, for example, you want to minimize according to the Swedish building code, then you need to translate this into money, and then you can do it. So the thing here, we will look at an example. So let's see here. So we have, let's skip here. So we have the utilities, these brown boxes, and we have the inside traders and outside traders. And then we have the contracts. It's these green arrows that we will add. So let's say that here at we want the inside, we want the traders to be able to buy and sell, or we call it purchase and export, with the utility providers. And then we have the trader contracts as well, so you can trade with each other. So now you see that it starts to get pretty messy. And then we need to agree upon prices. So this we add some prices. So it's 10 cents, 11 cents, 12 cents in one direction, and this is buying and this is selling. You don't get as much when you sell to the utility, but still it's possible. And then you get some pricing in between the traders as well. And then we need to define in every point of time what will happen. So for each time step, we need to know what these traders need, how much energy do they need or their excess. And then we see that we have some sellers, they want to sell, and we have some buyers. Okay, so let's try to set this up. And this is of course done automatically by EIs, but we have the contract rate plans that will define the order. So sellers, they won't buy from utility. Why shouldn't? So yeah, so you can get rid of some of the small arrows here. A few more. And buyers, they won't sell to utility. Okay, so we can get rid of a few more arrows here. Now it gets a bit more simplified. And then we have sellers, and they want to sell, so they won't buy from each other either. So can get rid of these arrows. Few ones there. And then finally, buyers won't sell to each other. They want to buy. So we can, now we have set up the case. So now we need to define who buys and sells. So buyers, they want to buy at the lowest price, obviously. So we can mark this is a buyer and he wants to buy at the lowest price, and that is 6 cents from this seller up here, the blue one. And then we have a few others. They are 7 cents. And then we have another buyer, and here we have the same price. So yeah, and then we negotiate, and the seller wants the highest price. So here we have a seller, and they can sell to the utility or to the buyer, and buyer is better. And we have another seller that have 6 cents, and a third seller at 7. So the buyer and the seller, they found each other now. Okay, so at 6 cents, done. So we have now a trading, and we do the same for the rest. So here we have a situation with the same price. We have this buyer over here, and yeah, for depending on how much the second buyer wants to buy, the third. The second buyer will probably need to buy from the utility at the high cost, depending on the situation. So yeah, it's not trivial, but if this is needed, if building the tenants, the building owner wants to be able to trade energy, this is needed. So you need to set this up, and by default we have this set up. For example, for the Swedish users, this is if you use a Swedish localization, this is probably not needed by default. So this is only when you're actually looking at the actual trading. Otherwise, this is kind of simplified. But yeah, it's great fun to look into these effects. But yeah, it's a lot to take in. So this is why I have spent so much time just presenting this for you. So a few final things, a few features. So for example, in EDIs 5.0, we now have the possibility to add non-rectangular objects on surfaces, for example, windows. So previously, if you wanted to model a window, looks like this, you would need to divide this in 2 or more rectangular objects to approximate this. And that now we have the possibility to draw irregularly shaped windows or whatever. It could be some other object as well, underfloor heating or something. And here we see that the mean average daylight factor is 3.6 when we approximate it with this. And here we get 4.1, the average daylight factor. So it has a big impact. It has some impact on simulation time as well. It's a bit faster. You get fewer windows. So yeah, could have a big impact on the result, but also, yeah, it adds up a lot of new possibilities. So, and this is of course a part of the new zone model as well. If you have the possibility to simulate irregular shapes, you need to be able to create them as well. So we also have a few final things that I will just pass through quite quickly, and that is we have an updated plant model with a lot of new features. We, for example, have the possibilities to have 2 hot water supply systems, for example, one for radiators and one for underfloor heating with bathrooms. Maybe we want 22 degrees here and up to 45 degrees on the radiators. This is very easy to set up now from the plant. We also have a lot of other objects, for example, these brine nodes that I really like. They are bidirectional and they are much easier to set up than the previous ones. We have variable heat pumps, speed heat pumps, We have a lot of new forms, for example, the new tank forms. We have circuit checking, so you cannot connect different objects with different type of medium, and a lot of other new things. So a lot of nice features in the plant modeling. We also have a completely new, not completely new, but a lot of new features or functions in the borehole models. Borehole model, I will just mention a few ones. We have, it's much easier to add patterns, for example, the borehole patterns. We have, it's over, oops, here it is. And you have a few examples. We have, we have ground temperature sensors, and we have a way to separate pressure drop components. So this is also something that I would like to mention. Then finally, see if I can share my screen here. No, I cannot. We have a new wiki. So if you go to help, we have a wiki page now, since instead of the old help file, and we also have a lot of usability and productivity features. And if you go to our website and search for news in EDICE 5, you can look at those as well. So that was what I would like to present, and I probably used up all the time, so there is not much time for discussions, but maybe we have some questions that we could deal with.
Pristine timing.
Victoria is looks a bit
typing
scared.
widely. Yeah, we got some questions. One of them was about the estimation of production produced energy of PV panels. If I see it correctly, it's about collision of usage and then generation. And then I'm widely typing already an answer. And then now the borehole model, if it's an included extension or if it's a separate model.
Yeah, so it's separate. So we have a simplified single borehole model in the Espoo plant that's available, but the other things are a separate module. I haven't used it myself. I'm a bit ashamed of that. I don't work personally with boreholes, so I'm not even sure about the pricing.
The extension is a separate separate component. You need to order it. Apart from IDIs. And then if the brine node is a replacement of the decoupler component, then yes, it is. It's kind of a combination of a valve and the decoupler. And the big advantage of it is that there is no need of defining mass flows, unlike in three-way valves.
Yes, and I also think you could log energy in them, can't you? I think you can. It's a lot of interesting features with them. So I like them. What else do we have? We have some electricity issues and log user problem. Oh, that is a tricky one. Yes, you can. We got a question about the usage of production locally and electricity, and it's not obvious to do this, but what my colleagues are doing are that they are separating the buildings and PV panels into separate models, and they can exchange the information using PRN files. That's one way to do it. And you can go both directions. You go from building to PV panels or PV panels to building, and there are some, I don't really know the details, but there are apparently pros and cons with both these methods, because since they are not consistent.
And there was earlier a question that concerned still the stratified zone models result visualization. You introduced the grid spacing, and it was the question that if it's what if it's not visible in the grid, or how does the grid and the calculated results correlate to each other?
Yeah, that is also so one tricky thing with the new zone model is that there are objects that are not necessarily visualized. So if you have a terminal and you don't have something that logs it, like you have a too crude this resolution grid. It's not really a grid, but let's call it a grid. So you could totally miss these objects if you don't have enough resolution, and this is you don't get that effect in CFD because you have, well, you can have a too coarse grid that could cause a problem. But this is the tricky thing about the new SOML. So that's why I said that, yeah, you can always use a stratification, but be a bit careful about, for example, if you have, in this case, hundreds of persons located in a single point. You still get the heat. That is correct, and it still affects the thermal the gradient in a correct way, but you could have a huge plume in the 3D view or not, depending on how you distribute these people in a floor plan. You could have 100 individual persons with 100 watts each, or you could have like everyone in the same position, and that would of course give very different visualized result.
So some accuracy in the grid is more critical in the stratified zone than in the
I would say so, yes. For visualization. Yes, so hopefully you will try these features out if that you need them. I understand that they are still a bit tricky. I think they are, all three of them. So if you have any questions, just reach out to us. We have the solutions companies. That's what we're here for. And even if I don't know all the details, my colleagues do. That's a good thing. So we will be able to help you out with these things. And it's still, this is the first release, so of course we need feedback as well. How to use this even more practical for your convenience. What services do you want to provide by having these possibilities? So that's something I would be happy if you reached out to us. Yeah, I have forgotten something, Victoria.
It didn't sound so, not to me.
No.
But if anyone else gets any questions, please let us know, as Max just said. Otherwise, I think our time is running wild and far. So thank you very much for everyone. Thank you, Max, for giving the presentation, and thank you for everyone to be present. The recording will come shortly today, still after this session, and let us know if we can answer any other unasked questions. And see you at the next one. Thank you very much for everyone, and looking forward to see everyone at the next coffee session. Bye-bye.
Goodbye.